So in this case, we are going to consider a continuation under the heat working with the unit of the gas processes. As we had before, remember we worked with the volumetric change. When you were working with the volumetric change in gases, that is the part actually where we considered the properties of a gas or the properties of a gas. We had these properties considered. So this part, guys, is just a continuation that we are going to have. So I'm just going to quickly go through the processes that we need to consider in our syllabus. There are actually so many processes that you're going to be having, but in our syllabus for engineering science N4, we're just going to consider three basic gas processes, just three basic. And these are the isocoric. So we have got the isocoric process. We have got the isobaric process. All right. We also have the isothermal process. So that's the isothermal process. So these are the three processes that you're going to actually be working with in our syllabus. But as we consider moving on with our power machines for N5, there we're going to be having power machines N5. We are going to be considering other processes. But in our engineering science for now, we're just going to be working with these three. So in this class, we're just going to quickly go through the isocoric process. In this case, we just need to consider what is happening. The process of isocoric, we have already referred these properties before when we were referring to the volumetric change of gases. Remember, there was a condition when we said V1 is equal to V2, dealing with the laws, but now we are considering as a process. So this is the process where we have got constant volume in terms of the volume, meaning to say V1 will be equal to V2. In this case, if the volume is the same, it simply means we do not have the change in volume. Because remember, the change in volume is supposed to be V2 minus V1. So if there's the same, maybe it's 5 minus 5, meaning to say we're going to get what? A 0. So for a constant volume, it simply means there is no change in volume in actual sense here. No change in what? In volume. So what will be the effect if there is no change in this volume? What is going to be the effect? The effect is going to be on the work done, because the work done is affected by the volume. So in this case, it is going to affect the calculation that we have on our work done, because there is no change in what? In volume. There is no change in volume. Remember, if we work with work done, let's say we've got a condition where we've got pressure, we can consider that work done like this. This is from our, we had this, a condition like this, is it N3? But let me just write it down. So if you are given the work done, when you have got pressure, remember, as we deal with the gases, guys, we said we're going to be considering volume, temperature, pressure. So there is pressure there. So the work done can be calculated from pressure times the change in volume. But we do not have the change in volume. That will be a 0. If you use V1 minus, V2 minus V1, that will give you a 0. So whatever that you're going to have there, meaning to say we do not have work done. So in a case of this nature, it simply means our work done will be equal to what? Our work done is equal to 0. That will be the condition. We do not have a change in what? In volume. A change in volume is not there. So if we do not have a change, therefore that's a 0. And that is going to affect our calculation now on the what? On the heat. We're going to talk about heat in the other part. Or let me just also consider here, but this is our science 3, guys. Remember the calculation for heat, that the total heat is equivalent to the work done plus the change in internal energy. All right. So that is our work done here. So if we are given to calculate the total heat, this is the total heat energy. And this is our work done. And we've got what? The change in internal energy. The change in internal energy. If we were to consider this part, it means our total heat is affected since we do not have the work done. The work done, remember, it is equal to what? To 0. So in this process of an isocoric process, it therefore follows that heat, which is our Q. So let me just write calculations here that you're going to need. So I'm going to go to the PV diagram very soon. So I was just going to refer to that one. So remember we said V1 is equal to V2 and work done is equal to 0. So meaning to say Q is equal to what? The change in internal energy. So therefore Q is equal to the change in internal energy, where the change internal energy, this change in internal energy can be calculated. It can be determined provided that we have got the specific heat capacity. The change in internal energy can be calculated. So it's the mass times the specific heat capacity times the change in temperature. Meaning to say the change in temperature, we are referring to what? T2 minus what? T1. That's the condition. That is the change in temperature. So if we are saying Q is equal to the change in internal energy, therefore in place of Q, we are going to write the formula that is Q is equal to the mass, specific heat capacity times what? The change in temperature, T2 minus what? T1. So this will be the consideration. And do not forget, guys, as long you are dealing with a gas, always the PV is going to work. So the PV formula can be used. PV is equal to MRT as we had in our volumetric change in gases. Remember, we also used the formula that has got the number of moles. PV is equal to nRT. But if you use this formula, know the properties on this formula, all right? It has got its own properties, right? So that is what actually you need. You're still dealing, guys, you're still having a gas. What we're just going to consider now is that there's what? The change in internal energy. We're talking about the work done, but we talked about this before. We talked about this before. So meaning to say any formula can be used where V1 is equal to V2. Go back to the volumetric change of gases and consider other formulas that we talked about there. It can actually help. And for a given mass, we are going to find out that the heat that we are going to be having, the internal energy, the change in internal energy will be measured in joules per kilogram because of the mass that is being considered. So you answer the question according to how it is given. That's the major part. Let us, guys, quickly have our PV diagram. All right, let us just have our PV diagram here. I might just end up saying a lot of things which are not necessary. It's like now I'm going into power machines N5. For N4, guys, there's nothing there. There's nothing. So like I said, other formulas like we used before, when V1 is equal to V2, remember, P1, it follows that P1 over T1 is equal to P2 over T2. All those formulas that we had. And what else? I think, yeah, that's it, guys. Let us just quickly have our PV diagram. So the PV diagram is pressure volume. That is the pressure volume diagram. Pressure volume diagram. We are working with what? An isocoric process, remember, where in this case, the volume is the same. So the diagram is actually representing the relationship between the pressure. The vertical axis is for pressure, horizontal axis is for volume. So remember, we are saying in this case, the volume is actually the same. V1 is equal to V2. How does that make sense? It means it's a constant. So if we've got points, let's say this is 0 here, our starting point, then this is 1, this is 2, this is 3, and so on. In terms of the pressure, what happens is that these processes, they are into two. They can be an expansion. Take note, they can be an expansion. They can be a compression. So let's start with a condition where the pressure is starting from a certain point 1 to 2, which is an expansion. So let's say this is point 1, point 2. If we have got this as our point 1, this one, it is supposed to also correspond in this manner. All right, let us have also here the same thing, 1, 2. So we have got something like this, 1, 2. It means, okay, let's consider the way that you understand. This is 0, 1, 2, 3, and so on. This is your V. If V is constant, it means it forms a vertical line like this. Remember, in your mathematics, guys, when you're dealing with the graphs, this is your x-axis, this is your y-axis. Where you have got the equation of x is equal to 1, it means x is equal to 1 throughout that line. X is not changing. So if this point is 1, we're going to have something like this. This is x is equal to 1. Throughout this line, x will be equal to 1. Y can change to say this point is 1, this point is 2. So you can say this point can be written as 1, 2. The x value is 1, 1, 1 here. The y value is 1. We move on, 1, 2. X is 1, y is 2. If y is 3, we move on, 1, 3, like that. These are points. But on these points, there's something about what? The x, which is not changing this one. It's constant. So this is the condition that you have. X, just like our V, on the what? On the horizontal axis. If the volume is constant, it means we are going to have a vertical line. That is the consideration that you must be very, very careful about. So let's say we are starting from 1 to point 2 in terms of the pressure, from P1 to P2. So what is happening in this case? The pressure is changing. As we can see here, the pressure was corresponding at point 1. This was P1 at this point. But what about the volume? It's V1. Okay? If we move to this point here, the pressure dropped. It's now P2. This point, the pressure is now P2. but the volume is still the same. We're supposed to write it as a V2 because the volume has changed, but the volume is not changing. We are supposed to have a condition, maybe we are at a point where the pressure is 2 like this, maybe the volume is 2, maybe somewhere like this, then we can join something like this where the two are changing. But in this case, the pressure only changed to a point where it was at this point 1, now it's at 2, but the volume is still there at 1. The volume, it was supposed to be V2 like this, but V2, remember, is equal to V1. So it is going to go back to the V1. It did not change. That is the condition when I'm saying it is constant V1 here. The volume did not change. It was supposed to be P2, V2, but it cannot be like that. So this change that is happening from P1 to P2, where we have got a decrease in pressure from a bigger value to a smaller value in terms of the pressure. It is an expansion. That's an isocoric expansion. That's an isocoric expansion. So the vice versa now is an expansion when we are starting with a smaller value in terms of the pressure. It can be like this. What I want you to take note is our starting point. All right. So this is our volume. This is our pressure. So if this point is now 1, we are starting from 0 going up 1, 2. We started with the smaller value going to a bigger value. All right. So the volume, guys, does not change. If this is 1, it's just going to remain there at 1. So P1 is corresponding with what? With V1 at this point. P2 must correspond with the V2, but there's no V2 because V2 is same as what? Is same as V1. So it's going to go back to that V1. Constant again, forming what? A vertical line. But the issue is we are starting from P1 going to P2 like this, from a smaller value to a bigger value. So this one, it will be a compression. So that's an isocoric compression. All right. So these are the things that you just need to understand. So the pressure here is P1, but what about the volume? V1. Here the pressure has changed. It's now P2, but the volume, guys, it was supposed to be V2 at a certain point, but we are still under the same value of that V1 because V1 is equal to V2. V2, there's nothing for V2. It is the same as what you had on V1. So that is what you're going to have. And if work done was going to be calculated, because work done is area under the graph. In this case, because there is no change that is happening, here we're just corresponding to say this one is corresponding to, in actual sense, guys, it's a straight line. It's just going to give us what is if it is here, just a straight line like this, here. There's no change in anything. So meaning to say the area is actually equal to 0. There's no work done. So work done is equal to 0, like we said before. So that is how actually you go about this part. You just need to understand how you are given the information. So let us say just have a question here to answer this type of a process. So if we consider this example that we are given here, we have got 2 liters of water at 30 degrees Celsius is heated to 60 degrees Celsius, ignoring the expansion of water. Calculate the change in internal energy of the water. The specific heat capacity of water is given. So they are asking us to ignore the expansion of water, the change that is going to happen in terms of the volume. So remember, in terms of the relationship of the mass, the liters, because this is volume, this one, 2 liters, it can be referred to the volume, back to the volume. Remember, we're talking about a cubic meter being equal to 1,000 liters. But this part, guys, we cannot work with the volume because remember, there are formulas. that the mass is given. The mass is what is used. So the question here, we can work with the mass. So what's the relationship between the liters and mass of water dealing for water? A kilogram is equivalent to 1 liter. So meaning to say we are given the mass. So according to the information, we have got the mass, which is 2 kilograms, 2 liters. It was 1:1. So if this is 2, this is 2. At this temperature, that's our initial. Remember our temperature, guys, in what? In Kelvin. So add 273. That's our initial temperature T1 of 303 Kelvin. Then to this temperature, which is T2, we add 273 again. It was going to give us 333 Kelvin. Ignoring expansion of water, calculate the change in internal energy. And we are given the specific heat capacity of water, our CV, as what? 4,184 joules per kilogram Kelvin. With this information, we're asked to calculate the change in internal energy. Guys, we've got a direct formula for this. The change in internal energy, the mass, the specific heat capacity, into what? The change in temperature T2 minus T1. So that was going to give us the change. The mass is there, which is 2. The heat capacity, 4184, times the change in temperature, which is T2 minus T1. So that's 333 minus 303. So that was going to give us the change in internal energy of, that was going to be 251,040, which is measured in what? In joules, of which, like I said, if we are dealing with this part, because we have got the specific heat capacity, which was kilojoules per kilogram. The kilogram cancelled with the kilogram there. So you can just leave your answer in joules as it is. Yes, you can write kilojoules per kg. All right. You can have this one as what? Joules per what? Per kilogram. To specify for any other mass that, for any other internal energy that you can calculate for given mass, for a given mass. But this is already, the mass has been applied. So meaning to say, we can just have our answer like this, in joules, because the mass has been applied there. We cancelled this part here. So if they specify, you answer according to the question. For sometimes exam, they can say, leave your answer like this. You cannot say, because I cancelled here the kilogram and this one, because it was per kilogram, so it cancelled. So you answer according to the question. But as for this, just going to leave it like this, or you can write in kilojoules. It's up to you. So that is how you simply attempt these typical questions. So just be geared up for other questions here. I'm not going to talk about this because we referred to this formula before. We used this formula before. So make sure that you go through volumetric change that we had in cases that so that you can have a recap on these formulas. But for now, that's it till we meet again.